Thank you very much for that introduction. Can I have a show of hands? Who here has taken antibiotics? Very, very unsurprising that most of you have. Now, assuming you were prescribed them, keep your hand up if you finished your course. Now, everyone put their hands down already, so I couldn't see. Hopefully, all of you did finish your course of antibiotics. So the question to the floor is, why do you need to finish your course of prescribed antibiotics? Yes, exactly. So don't need to ask more than one person perfectly. So essentially, we as humanity in the medical field, we are running out of antibiotics, partly due to overuse in both medicine and agriculture. And yes, exactly as he said, the reason that you need to finish your course of antibiotics is because if you don't, then you won't fully kill essentially all the bacteria in your system, and that they can learn essentially to resist the antibiotics and potentially come back stronger. And so we're seeing that, as I alluded to, you can potentially even get antibiotics without a prescription, and if you don't finish them, you're also fueling this development of resistance. And in the agricultural fields, we also see that there's mass usage, especially in meat production, and all of this can accumulate in the environment. So untreated waste coming from, say, a cattle farm, and also in pharmaceutical waste, all of this can accumulate in the environment and also contribute to this increase in antimicrobial resistance. And so essentially we really are at a difficult point where we cannot just rely on antibiotics themselves. And so my work is focused on reducing the bacterial burden of chronic wound sufferers. So a lot of the time chronic wound patients will have their wounds infected. And a chronic wound is, as this picture shows, it's an open sore, typically on your leg or your foot, and they can not heal for months on end or sometimes just indefinitely. And the management of these wounds is extremely costly. So personally, I'm focused on diabetic foot ulcers because people with diabetes are very likely to develop these wounds. But in general, non-healing wounds can cost the healthcare system globally over £200 billion in management costs. And one of the reasons, which I will focus on today, is the treatment-resistant biofilms that form within these wounds, and they severely worsen the problem. So firstly, what is a biofilm? It certainly isn't this. A biofilm is generally a thin, usually resistant layer of microorganisms that forms on a surface. They're not just made of bacteria, they can be made of many different things. And biofilms are everywhere. So one common example, if you've ever slipped on a rock in a river, that was most likely an algae biofilm. If you're not very good at cleaning your sink, you'll find a whole mixture of organisms in there, not just one. And everyone's favorite dentist will tell you to make sure you floss to remove the plaque between your teeth. These are all different types of biofilms. And one way to think of a biofilm is a city of microbes. So here we have an aerial shot of Paris at night, and on the right, which I'll describe in more detail later, is a close-up of a chronic wound biofilm. The scale is a bit different, about 300 million times difference here, but you can imagine that you have these individuals that are sheltered within buildings as sort of a model of the biofilm. And so how does a biofilm form? Well, you have these bacteria. You can just see that lozenge shape over there. You can imagine that they swim around with these wiggly tails, and when they find a surface, they attach to it, and then they begin to divide. And then as each individual divides, it becomes more mature and it becomes bigger. And then the bacteria, as part of their both attachment and as a way to protect themselves, they develop what we call an extracellular matrix. And this is both attached to the surface, but also coats them, and is part of the reason why they're so resistant to antibiotics, is because they block the penetration of antibiotics. One key thing is that at each stage of the biofilm's formation, the bacteria must communicate to each other. If bacteria didn't communicate to each other, then you can see that individual there would just split in two and divide, and then they would continue to do that, and then you'd end up with a pile of bacteria with no form, no regulation to it. You probably would have some individuals die, because you can imagine if you're all piling on top of each other, you'll run out of nutrients very quickly. And so bacteria must communicate to each other to get from each step, and especially once they get larger. And so they use chemical messengers to do this, and so they react to their surroundings, to other bacteria, and it's a crucial way for them to spread across the surface, but also completely leave if conditions are unfavorable. Alluding to that leaving, we call this dispersal, and as the name suggests, it's where the bacteria spread out from their biofilm form. So here we have what we would call a cluster of a biofilm, and some of the individuals will have signaled, okay, it's time to leave, and they change back into their sort of free-swimming form, and they begin to swim away. And this can be quite useful if we could potentially harness this, because we want to be able to reduce the burden on the wound. And one way you can think of it is if that city of microbes had a big typhoon coming towards it, that evacuation order would be very similar to a dispersal event, where all the microbes are leaving. So the question is, can we harness bacterial communication to our advantage? The answer is yes. I'm talking about nitric oxide. Nitric oxide is a potent signaling molecule that the bacteria produce themselves to inform other bacteria, okay, maybe the conditions aren't so good, as an example, or for any other reason, they produce it and say, okay, it's time to swim away, time to move away. So potentially they want to say, okay, there's not enough nutrients in this position, let's move across. Or it's like, oh, it's getting a bit hot here, it's really time to move. So they can tell each other, okay, it's time to swim away. And so what my research is looking at is, can we externally add this signal to encourage the bacteria to swim away from the surface they're attached to. So in the case of a wound, if you have bacteria that are starting to detach, they're both physically easier to remove, which is one of the key ways to treat the biofilm, is to try and remove it. And the other thing is that bacteria in this free-swimming form are much more susceptible to antibiotics. And so here we have a fluorescent image of a fluorescent microscopy image of a biofilm, and I'll be showing a few of these. So the color scheme is green is the individual cells of the bacteria, so the lozenge-shaped thing that I showed you before, and the orange wispy bits are the extracellular matrix that I mentioned before. So in this specific regard, you can almost think of it like the glue or the scaffolding. It both attaches and protects the bacteria. And so what happens when we add nitric oxide to the biofilm? Well, what will happen is, you can start to see, if we just keep your eye there, over time, once we've added this nitric oxide signal, you can start to see the structure will change. And so what's happening here is bacteria starting to swim away, similar to that cartoon I showed you earlier. But another interesting thing is you can start to see this ring of orange around. And so you basically have this almost lifting, this like volcano-shaped looking thing. So the orange is that sort of scaffolding that's been left behind as the whole cluster of bacteria begins to separate from the surface. So if we take a step back, about 10 times less zoomed in, we were already very zoomed in before, we can see, again, the same biofilm, and it's hard to see, but you can start to see there's a few individuals scattered everywhere, but a lot of the bacteria are in these very dense clusters or blobs. And in each of these blobs, there are thousands and thousands and thousands of bacteria. It's important to note that the biofilm can exist in all these different states across a surface. And so what will happen is, what will happen when we add nitric oxide again? And we can see this effect. As you start to add the nitric oxide, we start to get a removal or a lifting. You can see in the middle here that this blob starts to lift away, and we get a removal of a large majority of the bacteria. And so what I haven't shown you is, how do we actually deliver the nitric oxide? One problem with nitric oxide is that it's extremely unstable. So in air, in the presence of oxygen, nitric oxide will degrade within seconds. And so one of the things my work does is looking at ways to protect the nitric oxide until we're right at the point of delivery. And so in each of these pictures, one of the fluorescent channels, which I haven't shown, is actually what's delivering the nitric oxide. And so here I'll show you. We're looking at a two-dimensional slice of these three-dimensional spheres that I make, and these are liquid droplets with a lipid shell. And essentially the black center is this liquid that loves to dissolve gas, and that's actually how I deliver the nitric oxide, is as a gas. I flush it into these dark cores, and then the yellow ring on the outside is actually a lipid shell, which both protects the liquid inside, but also slows the release of the nitric oxide as it follows a concentration gradient to come out. And so what I'm looking to do next is combine both the delivery of nitric oxide with antibiotics, because we do have evidence that with different delivery particles, we have evidence that if you combine the two, you can reduce greatly the amount of antibiotic that you need. And other directions we're looking at is, some people are looking at ways to completely remove the need for antibiotics, because we are running out at the current state. And some people are looking at using physical methods to physically scrub away the biofilm. And other people are looking more into the direction of the chemical messages that I talked to you about, improving the way that we can sort of guarantee that the biofilm leaves the surface. So thank you very much for listening, and I'm happy to take any questions.